Thank you very much. Good morning, everybody. Let's continue. Last time we started looking at routers, high-speed routers, and we started first of all by clarifying the term that is used in association with routing, and that's the process of routing and forwarding are two separate processes. The routing, again, is the process of creating routing tables, networks across the internet, as we'll see. So the routing is the act of building routing tables using routing algorithms. We will classify routing algorithms shortly. For the routing, there are no incoming packets. So there is no incoming need to have a routing table associated with what? With routes. Forwarding is the process when the packets are incoming to the router will what? Will the forwarding, transferring the packet from an incoming interface to an outgoing interface. Of course, after consulting with some of the forwarding functionalities that we looked at is checking the header, trying to figure out what the destination IP address is. It performed checksum on the header. Checksum means whether the header has errors or not. It's selecting the network protocol, whether it's IPX, any other types of networking protocol that is being used. Decrement TTL field. Every time a packet goes through a router, the router will decrement the TTL field. Type of service field to prioritize the packets to what type of service is each packet is as processing option fields, forwarding the route to the packet, forwarding or routing the packet to the next hop. If the packet does not fit into the maximum transmission units of the frame. Routing functionality, these are the forwarding functionality, is to try to exchange information or routing information between each others, keeping track of network management statistics, including how many packets are being transferred, what is the length of the packet, what is the type of the packet, nation IP addresses, a matrix, and so on and so forth. And, of course, the tunnel management. We'll speak about the tunnel. Okay. We saw just a diagram of how do routers switches are some big routers. Those are heavy routers, heavy-duty routers, which are referred to as what? The core router. Responsibility is to transfer the packets across the ISP networks and between ISP networks. Home are a small scale. These are routers at home, small scale routers. They have limited, if we saw a couple of diagrams for a Cisco router and for a Juniper router, and you can see the 160 gigabits per second. By the way, this one here right now is 3 or 4 times as much. Is relatively, it's not up to date. And with capacities right now, we have 400 or 500 gigabits per second. So 3 or 4 times faster than this one. Clear? To be able to support the high volume of packets that goes into the core network. Also, the power dissipation is relatively large. At core, and these are the routers, the high-speed routers associated with them. They are, remember, distinguish, we will see that in just a second, between the edge routers and the core routers. In the edge routers, all including the marking, the regulation, the policing, all the shaping, traffic shaping takes place. Just basically a transport mechanism. This is a snapshot. We looked at the POPs, presence, where the traffic is going to be exchanged. You can see that we have a whole bunch of routers interconnecting different POPs, exchanging traffic from one so forth. This is the basic architecture of the router, and you can see that is the switching architecture that we have talked about since a couple of weeks ago. This is along with it. We have we have a bunch of interfaces. This one, you will see it here. You see all of these things? All of these, it's like books. You see those? Those are interface cards, with different speeds, different technologies, and so on. And of course, the switch by the routing controller and the management controller. And each one of these has a processor associated with each interface. If you look at the arc, again, as I told you, it's divided into 2 steps or 2 planes, the data control plane. Again, the difference between the control plane and the data plane acting as when on a packet per packet basis. Whereas the control plane does it what? Does it one time for all and for all. In the routing plane, you deal with what? With admission control, you deal with congestion control, with reservation, like RSVP, for example. This is all done in the control plane. In the data plane, you do leasing, traffic regulation, traffic shaping, scheduling, switching, and scheduling, the weighted pair queuing here, for example, the random early detection, and so on and so forth. All of them in the what? In the database. It's per packet processing. Clear? Okay, good. It here in the incoming, for example, these are the when the packet comes, forwarding the switching will interconnect them from what? From an incoming port to an outgoing port, where they are going to be what? Output queued buffer, waiting for what? Waiting for scheduling. Scheduling means what? Deciding how you are the packets are going to be served to the outside world. This is a generic. Let me show you the different generations of routing, and then we'll go back. These are the what? These are the first generation IP routers, the old IP routers, if you would like. You see in the back plane, a shared back plane, the CPU, the central processing unit, and the buffer memory. And in every card, this is a line card, there is a what? The line interface. MAC stands for what? The medium access control, attached to a what? To a high-speed bus here. Okay. DMA, the direct memory access, when the packet comes in here, it will go directly to the what? To the memory. Everything is done where there was no processing done in here, or very little processing. All the processing is done in the what? So when the packet comes in here, by the way, most Ethernet switches and packet routers are based on this idea. This suffers from what? The bottleneck could be the what? Could be the CPU, could be the card, could be the I/O bus. This is the I/O bus here, and so on and so forth. All of these. It's like you are going to put all of these line interfaces. Is this one? The CPU and the memory. That's the first generation. The second generation, what did they do in here? They added a local buffering memory. A local buffering memory. So in here, the previous one, there was no memory in here. It's direct memory access. Everything will be stored in here. The card, they include what? A local buffer memory, local buffer memory, local buffer memory. But the plane was still a high-speed bus. Still a high-speed bus. Clear? But in this case here, you don't need to go through the back plane every time. You are going to what? You are going to use this memory to decide what? To decide where is the outgoing interface going to be. Clear? It's not the processing. It's not all the processing is going to be done in the back plane. This is the second generation IP routers. Third generation IP routers, what did they replace? They replaced speed bus by a switching architecture. Clear? By a switching architecture. So we have what? We have, and then what? And then the CPU card in here, a separate card in here, and the line card will go through one to the other. For example, from here, it goes to what? It goes to here. Did you get the place? The high-speed bus is gone. The high-speed, we have what is known as what? Parallel paths. You can have parallel paths from where? From each incoming interface to each out. And then the last generation, which is the fourth generation, switches or routers, as what? Clustering and multi-stages. So huge stages of routing. All of these are what? Are the interface cards, and they are interconnected to a what? Back switches here via what? Via high-speed fiber. All of these are what? Are fiber stuff. You can see number 1, 2, 3, 4, 5, 6, 7, 8. All of these are what? Are line cards interconnect the control units in here, or the switching architectures via what? As fiber. All of these are fiber stuff. Clear? Okay, good. Now, these are just an example of some commercials. The capacity for somewhat different types of models for Cisco's and Juniper, and you can see the huge speed, the 720 gigabits per second. Currently, they are experimenting with what? 1 terabit. Tera means what? 10 to the what?
1 o'clock.
10 to the 12 bits per second. Clear? A huge speed, gigabits per second, 640 gigabits per second. And you can see also the what? See also the memory is getting higher and higher, and so. Some types of commercials routers. Okay, so let's get back to the routing architecture. The packet will be arriving to the router. The router will look up the header and from the address table or routing table determine what is the next hop router. This one will ask, this is the IP address. From the going to get what? The next hop router. You update the header. Updating the header. Every time you go, it goes through a router, the header is what? Is updated. IP addresses do not change. Other fields in the IP header will change. So you need to what? You need to update the header and then you need to join waiting for outside scheduling to begin before you go into outside. This data and this data did not header did change. The header did change. Gets updated a lot bit. The first generation or the first router and so on. So these are some of the done in the IP layer. In the IP layer, you can see some of it are what done in the control plane, in the data plane, and routing management, ICMP. ICMP stands for ICMP, the Internet Control Messaging Protocol. That's error reporting, what is known as what? Error reporting. Sometimes, for example, if TTL reaches 0, an ICMP message telling you what? Telling you that the packet it has reached its limit. Sometimes you enter, for example, a URL which is not reachable. You get an ICM, but this URL is not usable, it's not reachable, and so on. So clear? After it processes everything, then it will deliver the contents of the packet either to the TCP, UDP running in the transport layer protocols. From here, it's getting it from what? From the frame layer. Clear? Whether it's Ethernet or whether it's ADSL or token ring and so on. So to summarize, the per packet processing in IP routers accepts the packet arriving on an incoming link, look up packet destination forwarding table, identify the outgoing ports, manipulate packet header, decrement TTL, update some, and so on and so forth. Send or switch the packet to the outgoing, specify and buffer the packet in the queue, and then transmit the packet on the outgoing link. Sequence of place. Okay. In the routing table, what do you see the structure? An IP address, host address is 32 bits long. When we get to the 6, we will see IP version 6. It's after the break. After the spring break, we'll get to the IP version 6. I will give you, you will see that the address instead of 32 bits, it's 128 bits long. Clear? It's the 32 bits. The network address, of course, is what? Less than 32 bits. Less than 32 bits. Now, the reason that we are talking about what? We are talking about the network address because this the host IP address. The network address is less than, total is 32 bits. The network address is less than that. Network address, why? Because the router, the network address or the delivery process, they are not going to be looking at what? At the entire IP address part. It's next hop router IP address. The next hop router IP address reach, if a given router cannot reach the destination by itself, it will be delivered or it will forward the packet to a router on a directly connected network. When router, next hop router means what? Those two routers are what? Are attached to the same network. All right. You also see in the routing tables a whole bunch of flags. It's network flags or host flags, spaces, and so on. And then, of course, the network interface card. This is how you see it, and it's just an example of a routing table. You see a whole bunch of what? A whole bunch of addresses, the host addresses, multicast addresses. We'll talk about multicast routing after the break. It's multi-loopback addressing. Loopback means what? Testing, transmitting. You are transmitting a packet to yourself. Clear? This is next hop routers. These are the gateways. A whole bunch of what? A whole bunch of addresses. It's some flags. What? UGH, for example. What does it mean? The router is what? Is up. The router, what? H, the route is a what? Is a host. D, the route was what? Redirected. The route is what? Suppose you do have like this. Suppose you have a network, and then there is a router here, R1, and there is another router here. This is the host, A. Now, what do you need to configure your machine with? Your machine with the what? With the IP address of a default router. You need to choose a what? A default router, whether it's what? R2. Now, suppose you chose R1, and you transmit the packets like this, like you are transmitting it like this. R1, if he believes that you would have a better route, this one will what? Redirect the route to what? To R2. This is called what? Route redirection. It comes from what? R1 all the way to R2, and R1 inform A that you are better off if you go through R2 rather than what? R1. This is called route redirection. Clear? Different types of interfaces, all of these types of interface, and this is what, how many times have they been used? Clear? So a typical routing table look like this one. Let's get into the details right now. Now, first of all, we need to understand the concept of hierarchical routing in the internet. It's just an overview. See what I'm talking about. Okay. Why did they opt for hierarchy? Why did they opt for hierarchy? Hierarchy means what? The internet into multiple what? Into multiple regions. And let every region what? As an autonomous system. AS stands for what? An autonomous system. So they divided into several what? Several networks. They refer to it as what? As the internet consists of a large number of separately managed networks, each one under what? A given administration will set the policy, the routing policies within the autonomous system. So internet is made of separately managed networks or internetworks interconnected together by means of backbone networks, the backbone server line. Each separate network or internetwork is treated as an autonomous system, and every is given an address. Every autonomous system is given an address, and that address is a unique 16-bit ID, which means how many autonomous systems there are up to. The number of autonomous systems is up to what? 2 to the 16, which is 65,000 and change. And even this one here, what? They are running off ID addresses for autonomous system. An autonomous system may be a what? A customer network. You do have a network in a corporation. That's an autonomous system by itself because it's under the administration of it's the under administration. It could be an ISP. ISP is regarded as what? As an autonomous system. It could be backbone provider. Backbone provider, those are the high speed national service provider providing for transport packets between ISPs. Each autonomous system representing domain. Each autonomous system represents a what? A routing domain, or identify a what? A routing domain. So we have what? Multiple domains. In every autonomous system, we have multiple domains. Autonomous system chooses routing policies or routing algorithms within the autonomous system. There are minimal information, as we will see in just a second, between autonomous systems. Each autonomous system is represented by what? By a routing domain. Different types of autonomous system, The first one is called what? A stub. Let's see it separately, what I mean by it. A stub autonomous system. A stub autonomous system. This is a stub. This, we call it a stub autonomous system. A stub autonomous system connection to another autonomous system. This autonomous system has only a single connection to another autonomous. This is a stub. This is a stub. Clear? This one is not a stub. Why? Because it is connected to what? System. Clear? A stub has single connection to another autonomous system, and all that is local. All the traffic is local, i.e. the traffic originates or terminates at what does that mean? What does that mean? See these autonomous one that is referred to as a transit, their functionality or their traffic, the traffic that goes in the systems might not have been what? Generated here nor destined here. In the autonomous system generated here, all the traffic is what? Is destined here. In other words, it's not this one to what? Carry traffic of another autonomous system just as a transit. It's the traffic is either generated here or what? Or terminated here. Traffic originates or terminates at Multi-homed autonomous system is an autonomous connected to multiple other autonomous system. We call it what? Multi-homed, several homes, several connectivity. A multi-homed autonomous system has multiple connection system, does not carry non-local transit traffic. This one again does not carry what? Transit traffic, either originating here or what? Terminating here. Clear? Carry the transit traffic. And then we do have the transit autonomous system. These are the transit autonomous systems. Have what? Multiple connectivity to other autonomous systems. Look at this. Have this connection, this connection, this connection. And they carry both local and what? And transit traffic. Both local and transit traffic. More time. Did you answer what transit traffic means? Traffic means what? That goes into this autonomous system, originate from some and destined to what? Somewhere else. It's going through that autonomous system just as a what? Just clear? Okay. Now, so these are the autonomous applications. Now, let's classify routers so that we understand what each function. We start with the simplest one of them, which is called what? A subnet router. A subnet router that only covers what? Operates entirely within a single what? Within a single network. When used. Now, what does that mean? I have a network. I'm going to divide it into what? Into multiple subnets. There is connected a what? At least a single router, and that router is referred to as a what? Subnet router. It is to carry traffic from and to that subnet. Its responsibility is to carry from and to that particular subnet. We call it a what? A subnet router. Operates entirely within a single subnetting is used. Then we have what is known as what? Access router. Access router or gateway. The name, disconnect a what? An access network to an interior router or what? Gateway. So what does that? If you do have this, this is simple. Okay, and this is the access router. This one is called the what? The access router gateway. There are other routers in here, but they are all what? Internal. All of them are what? Subnet routers. I got multiple network here. It's a network here, network here, network here, and so on. So the access, they go through what? They go through the access router or the access network to an interior router or what? Gateway in the ISP. The interior in the ISP networks, those are routers or gateways used to interconnect networks within the same autonomous system. So we have what? We do have an autonomous system here. This is an autonomous, and we do have what? Multiple networks within the autonomous system are what? There are routers attaching them. These are called what? Interior routers. And then we have what is known as what? Exterior routers interconnect. Exterior routers interconnect autonomous system to what? To other or to the backbone. So we have, let me show it to you here so that you can see. What do I have here? An autonomous system, multiple networks within the autonomous system, another multiple networks within an autonomous system. What do we have here? This one is connecting to the core backbone. This one connects to the core backbone. Called what? These are called the exterior routers. These are called what? Interior routers. Use different protocols, as we will see in just a second. These, every one of them is referred to as a domain. This whole thing is a what? One routing domain. That's another one. Routing domain. Internal routing here does not need to be the same. They use different algorithms to generate routing tables within the autonomous system. This is from a layered architecture point of view. What do you see? This is the site network. This is the host is running what? Is running the entire layered architecture, the application layer, the IP layer, ARP here, the link layer, the physical layer, and so on. So this is the access gateway or the default Think about this one as a what? Again, you have the what? The physical layer, the link layer, and then the what? The IP, the ARP. This is what? This is gateway. Interior gateway is the one that what? That interconnects network within the autonomous system. And again, what do you see? The physical layer, the link layer, IP, IGP stands for what? Interior gateway protocol. Interior. When I say interior, means what? Within the autonomous system. Within the autonomous system. Clear? Okay. This is the autonomous system. Then what? What is this? That's the exterior gateway. What is this one is running? Physical layer, link layer. He has two sets of what? Two sets of routing protocol. One of them is what? IGP, which is the interior gateway protocol, to work with who? To work with, communicate with who? To communicate with this one, the interior gateway protocol. And then what does it? He has EGP, which is the what? EGP is the what? Exterior. Protocol. Communicate with who? With other autonomous system. Do you see this autonomous system? This site network, what? Within the autonomous system. Whereas this one here is another autonomous system. EGP, or IGP. IGP is used to communicate between routers, between networks, within the autonomous system. This one is between autonomous system. So you can see that some routers have what? Multiple routing algorithms implemented in them. Reposition, their location, and their functionalities. An autonomous system, by the way, in my cases, it does have more than what? More than one exterior gateway, which means what? You have a point from the autonomous system to a what? To another autonomous system. Multiple exit point, as we'll see in just a second, GP. Okay. Now, do a routing table. Hosts themselves, do they have a routing table? The hosts themselves, they maintain something to enable them to forward the packets to other home network, on the other, to other hosts on the same network, to a subnet router if subnet is used, or to access router or gateway if subnetting is what? Is not used. Clear? So even a host has a limited routing table. One more time, what is the purpose of this routing table? In a host is to communicate with what? Other hosts on the same network, is to what? To access a what? A subnet router, the router that is attached to that network, and what? To connect to the access router if the reason is to go of the network to which you are attached to. Maintain sufficient information, every one of them sufficient information. In other words, a router, listen to me, your router at home, if you look at the routing table, do you see entries in the world? Of course not. So what I'm trying to tell you is that what? Is that every one of these devices, the host, has just enough information, sufficient information to perform its functionality. So for example, a subnet router maintains information to enable them to forward the packets to other subnet routers belonging to the same what? Same network, yes? Or what? It reaches with what? The access router. They don't worry about what? They don't worry about entries of networks which are outside their own network. Clear? Everyone is only interested in their own network. These are the subnet routers. Interior routers. What do they have? Interior routers. Remember, interior routers are the ones that interconnect different networks within the what? Autonomous system. This one. Again, one more time. Connect different networks within system. Within an autonomous system. Okay. What do they need? We need sufficient information to enable them to forward packets to other what? To other interior routers or gateways. To their own what? to their own access routers or gateways. In other words, backward. If the access routers, look at the access routers. Sorry, subnet routers is enabling to what? To go to the access routers. The interior should be able to find what? Should be able to go back to the access router, to their own, and to other interior routers or gateways, and also to what? To exterior routers or gateways within the autonomous system. If you look at this, one more time. If you look at this is the interior router. Clear? Interior what? Interior routers or gateways. To have information of how to reach this one. Not how to reach what? This one. But how to reach. Did you get my point? Did you get my point? This one needs to have information of how to reach this one. This one. Okay. The exterior router, this one, needs to have information of what? Other exterior routers in different autonomous systems, and also how to reach what? An interior router. In other words, this one needs to have an information of how to reach these interior routers. An interior router, it has to maintain sufficient information forward package to an interior router or gateway is destined to the autonomous system to which it is what? To which it is attached. Embedded or destined to the autonomous system to which it is attached. So for example, if this receives a packet that is destined to this network, if this one receives a packet that is, this one needs to what? Needs to have an information about what? How to reach this network. He needs about what? About all of these routers. Clear? That's what it means by saying what? An interior router packet is destined to the autonomous system to which it is attached. Okay. The routing algorithms, we have seen these classifications, and we have two types of classifications of routing algorithms. First of all, intradomain. Intradomain means what? Within what? Within an autonomous system. Within them, we have two dominating routing algorithms, which is what? Which is the distance vector routing. That stands for what? Distance vector routing or routing information protocol. And what? OSPF, which stands for what? Open shortest path first. Now I'm going to review this today very quickly. I don't want to spend because we have already taken them in what? In perspective. Our interest in this course will be on border gateway protocol, which is called what? PGP. The PGP, the one that is used within the what? Is used between what? Between autonomous systems. The protocols are that is used between this one and this one. So we will spend all the time on the PGP to understand it's a very complex protocol. But first of all, I need to review this very quickly so that we get. So we started with the intradomain routing, and intradomain divided into what? The distance vector. We refer to them as what? DV. DV stands for what? Distance vector. Let's see if you remember this from 450 quickly. What does a distance vector do? What is a distance vector? This vector. Every router will what? Will exchange information, routing information, neighboring routers only. Neighboring routers means what? This means the routers that are attached via direct links to that, to them. Every router will what? Every router will exchange information, routing information with adjacent or with neighboring routers. What is that information? What is that information? That what? The distance between that router and every other router that is known to that router. To the clear? Okay. So the distance vector routing uses a distributed algorithm allowing to build up a routing table of its own. That's what it's referred to as a what? As the vector. The routing table, the shortest distance. The criteria is what? Is the shortest distance. That's why we call distance vector. To reach all the network IDs in the what? In the internet network. Within the what? Within the autonomous system. Within what is the shortest distance to reach all the network IDs. Initially, Each router is the network ID of the networks that are attached to it. At the beginning, does the router know about a specific router, a given router? Does he know about other networks or not? At the beginning, he doesn't know about a beginning. He only knows the network ID, the net ID of the networks to which it is attached. Also knows the distance to what? To the neighboring routers. Neighboring routers that are what? The ones that are what? That are directly connected to them. Each router exchange its, which is the distance vector. Each router exchange its routing table with its distance vector with neighboring routers. Based on this information, every router updates its routing table accordingly. Router, for example, R2 receives a what? A distance vector from what? R1. R2 will what? Update its information that it receives from R1. And this process, again, is repeated until what? Until you get the general information. Before I show you an example, let's look at the algorithm itself. Router maintains a distance vector. What? The list of destination cost entry. What does this mean? If the destination network is this, then this is the what? This is the cost, or this is the what? The distance, and this is the cost. The distance to that destination. Send a copy of its distance vector to all the neighboring routers only to the neighboring router. The receipt of a distance vector, the router determines its new distance vector based on this. To a new network, the cost to a new network is the minimum of the cost, the old cost to that plus what? The cost to go to what? The cost to go from V to what? From W to what? V to what? The cost of W. Clear? In other words, each router will say the following. This is vector. Every router will calculate the distance between itself, every other router, the one is at short distance. Take the one that is what distance. This cost of V means what? How do you reach V directly? How to reach how to reach what? How to reach V via what? Via W. Clear? Via W is the one that is what? That is the shortest distance. That is what is proportional to M times N, where M is the number of links and N is the number of what? Nodes. See that the complexity of the algorithm increases as the number of links increases, as the number of what? The complexity of the algorithm will what? Increase as well. Let's take an example. Again, this is from 450. You have seen it. This is just a quick review. How many routers do we have here? We have the distances are what? 1, 2, whatever, 2, 2, 1. This is connected to what? One network. This is another network. This is a third network. And this is the fourth network. And let's assume the network I 2, 3, 4, and what? And 1. Again, as I told you, are what? Are interior routers within the same what? Within the same autonomous system. All of these networks are within the same what? Autonomous system. Clear? Okay, help me with this. Can you zoom back, please, a little bit? Just a little bit. Yeah, thank you. Okay, let's look at R1. What does he have? What does R1 know? At the beginning, R1 knows only that it's what? Attached to network ID 1, which is this one. The network ID 1, which is this one. And he knows that the distance to R1 is what? Is 0. Distance to itself. Same thing with what? Same thing with R2, same thing with R3, same thing with what? R4. Now, listen. R2 and R4 are neighbors of R1. R2 and R4 are neighbors. What do they send? R2 will send its distance vector to what? To R1, and R4 R4. R4 will send its distance vector to what? To R1. What does R1? Listen to what he updates. He updates. Network ID 1 is what? I'm going to reach it at a distance of, because I'm attached to that network. Network ID 2, what does he say? He said the next hop router is what? R2 and much? 2. The distance is 2. Did you get this or not? How did he knows this information? Because R2 told it I can reach what? Network ID 2. What? Then I can reach network ID 2 through who? Through R2. Network 4, he can reach it what? Through R4. And the distance is also what? Clear this one. Okay. Now let's look at this one. What is this one? This one is R2. Where is he getting the distance vector? He gets the distance vector from all of them. R1 and what? R4. Initially, what does he know? R2 only knows what? Only knows network, because it's directly attached to it. After this one and this one and this one communicate their information, they update its information as follows. Net ID 1, next hop is what? R1, its hop is what? 2. 2, this one stays the same. 3, you go to what? 1. 4, you go, the next hop router is distance to what? To the next hop router is 1. R4 is what? Is if you want to reach network ID 4. Same thing with this one and same thing with this one. You update. Now, then what? Then comes the next. What does this receive? Again, he received what? R2, R4. He received this. Let's see if you can help me. Did he get this 3? Where did he get this 3? How did he know that he's get 3? Because now he is receiving from who? From R4. Clear? R4. And what? Both cases, he has what? He has the distances. Sorry, he has the answer to the information that they can reach what? Network ID 3. So what did he choose? Why did he choose R2, 3? To reach network 3 via R4. Via R4, what is the distance? What is the distance between R1 and R4? Which means the distance between R1 and 3 is how much? Yes? Whereas, what is the distance between R2 and network 3? 1. What is R1 and R2? He would choose what? He would choose this path, the shortest path. So the next hop, 3 here. If the network ID, if the destination network, then the next hop is what? The next hop is what? R2. He will send it to R2. Clear? Rather than what? Sending R4. Because if he goes through R4, the distance will become what? Will become lost this one. Clear? Okay. And so on and so forth. You can read they are just what? Updating those routing tables. It takes some time to converge. The longer the network is, the more what? The more nodes it has, or the more length. The complexity of the protocol becomes what? Becomes high, and the algorithm becomes what? Non-scalable. The distance vector will what? Will increase as the number of devices, or as the number of routers in vector will increase as well. Okay. The other type of what? The other type routing protocol is called what? The link state. An example of this is, again, the OSPF, the open shortest first. The link state protocols, let's summarize it, try to understand it. The link state protocols, each router in the network is assumed to know the state of the links to others. Each router in the network is assumed to know the state of the links to all of its neighbors. For example, the operating status, whether the link is operating or not, the bandwidth is available to that connection, how much delay, and so on and so forth. Each router will disseminate information via reliable flooding. It needs to make sure that the flooding is what? Is reliable. Each router will disseminate. Disseminate means what? Disseminate means what? Exchange. Disseminate information via reliable flooding of the links. We call it what? Link state. Link state packets, which is the information about its link state, other routers, neighboring routers in the network. So what does that mean? I am a router here, for example. R1 connected to what? Multiple other R2, R3, 4, and so on and so forth. What is this one? This is, again, system. This is an interior routing protocol. R1 will broadcast, not only to the neighbors, it will broadcast information about what? The state of its links. So, for example, R1 will say what? Links attached to what? R2 attached to what? R3 attached to what? R4, these links are, for example, are operational. The cost of them are such and such, the bandwidth. All of this information are disseminated. Notice, by the way, when they are disseminated, in reality, they are sent to the what? To the neighboring routers only, and the neighboring routers will what? Relay it to their neighbors, to their neighbors. Every router will what? Will do its job to disseminate the information about the links and routers to all other routers. When they create, each router will disseminate, again, via reliable link state packets. In each case, every router will have enough information. Every router will have to create a what? Or to build a what? A map, a complete path map, be able to construct the what? The shortest path, spanning tree. What is a spanning tree? Spanning tree, a spanning tree is a what? Is a tree with no what? No closed loops, which has no closed loops. It will be able to construct the shortest to everyone, from itself to every other router. What is the algorithm? Do you remember the name? The Dijkstra algorithm. And again, we have discussed this. I have no intention. Again, we have already discussed it in EE 450, and for those in EE 550. Anybody taking 550? Is this being discussed? What you go into the discussion of that algorithm again. By the way, also in CS 551, in other words, you will see this algorithm again and again and again in multiple classes, which is creating the shortest path spanning tree. But did you understand what that means? Information to create a map? What does that mean? If every router is going to exchange information of its links with every other router in the network via reliable flooding or dissemination, every router will create a map. You don't need to exchange what? Routing tables with other routers. You create a map yourself, and from the map you can figure out what is the shortest path containing every router with every other router in the network. Okay, so in here, its algorithm, the router maintains a database of this that describes its links. Router floods a copy of every link state package throughout the network, sequence numbers, and duplicate elimination to control the flood. Why is that? Why does it use sequence numbers when they flood the link state packets? Why do they use sequence numbers? When you are flooding, this is a network. One more time, let's make it a little bit smaller. Okay, this one is what? R1. When R1 is flooding the information, the network, with the state of its links, the broker come this way. Follow me here. This. Then what does this one do? It relays it to here. When this one receives it from here, what does he do? He relays it here. He relays it back here. No, not. It's reliable flooding. You flood everywhere. You need to what? You need to sequence those packets. The reason for that is it possible that the second update or the third is received before the first update? It is possible. Why? Because inside the network, the packets, no guarantee that the packets will follow the same route. There is no guarantee that the packets will follow the same route. So I know whether this update message, whether this recent message or what, or it's an old message. Clear? Notice, by the way, in here, the router does not need information about its link state every time. It has to do it only if there are changes, in its link state database, or period of time as what has expired, usually about an hour or so, and then it will disseminate info routers, and your routers will be able to learn about them. Is it possible that this one will receive duplicate link state packets from here? He will receive it from here. There must be what sequencing of the packets to what disregard the old one. I repeat, disregard the old one and keep the new one. Router applies the Dijkstra algorithm to find the shortest path, and the TA will give you an example on this just to refresh your memory. From 450, we have already taken this in 450. And the shortest path based on what? Based on the number of links rather than based on the number of. Why? Can you tell me why? Why the shortest path routes based on what? In order of proportion? O stands for what? Order of. M log M. Why? M log M. Where M is the number of links. This one depends on the number of links. Of what? Not the number of what? Nodes. Why? That's why we call it what? The link state. Every router will disseminate information about the state of what? Its links. Links it has. The more links it has, the more links it's attached to, the what? The larger the information. It does not depend on what? How many other nodes are there in the network. Agree? So the complexity you can see, compare it with the previous one. The previous one was proportional to the M times what? M times N. The log M, of course, is what? Is to identify or to address the M links. How many bits do I need to identify each one of them? I need a log M bit each one of these M links. Let's look at the comparison in here. In a router, you are going to send the distance vector to their neighbor, whereas in here, in the link state, you are going to what? You are going to broadcast the link state path routers, not only the what? Not only the neighbors, allowing the link state to create a map of the network and execute the Dijkstra algorithm, the shortest distance spanning tree to every other router in the network. Clear? Clear? Let's get to the more interesting part, which is the what? Which is the interdomain routing. Interdomain between autonomous system. Now, before we get to the detail, this is the next set of charts, which is what? Which BGP works. Let's look at it in general. BGP, look at it in general before we get into the detail. Excuse me. BGP, which is the Border Gateway Protocol. Again, this one is used by, let me see. Huh? Used by this guy. I recall this only by this guy, not by this guy. The distance vector and the link state are used here. We are now talking about what? The problem. Let's see if you can help me here. Is this discussed, by the way, in 550? Huh? A little bit. So right now we are going to expand on it. By the way, it's also discussed in 551, but we will expand on it so that in 550. No, not 450, 550. No, okay. So, but in any case, let's try to understand it and rather than some detail. Border Gateway Protocol. This is the protocol that is used for routing between ISPs, between the service provider, the internet service provider. This is the protocol that is used to put packets across the what? Internet. Across the internet. Are you following me on that? Hundreds of routes makes the what? Makes the Border Gateway Protocol clear to reach every weapon or every destination in the world. Did you get my point or not? Okay. But it is only autonomous system. That's the whole idea about the hierarchical routing. It does not need to know the destination network of every site in the world. All what they need, for example, I'm an autonomous system. I need to fit a path or a route to another autonomous system. I don't need to know the detail of every router within that autonomous system. I just need to know the information of how to reach the protocol of that other autonomous system. Okay, let's see if you can help me here. This is just an overview. We will leave it till next class, or this class if we do have the time. Let's see if we can. One or more gateways in each autonomous system. One or more gateways in each autonomous system will function as an exterior gateway for that. What does this one tell you? It tells you that every autonomous system could have multiple what? Could have multiple border gateway protocols. Clear? Could have multiple border gateway protocols. The exterior router communicate with other interior routers, inside the AS using what is known as what? IGP. They call it what? PGP. I wish between IPGP and EPGP. EPGP stands for what? Border Gateway Protocol. IPGP stands for what? The Interior Border Gateway. This one is used between what? Let's get the, what is this used? IPGP. What is it used between who and who? IPGP. The Border Gateway Protocol is used for this one to communicate with what? With these routers. Get my point or not? Yes or no? Yes. Okay. I need you to understand one thing here. And the link state is used between what? Between these. And that or not? It's not, this one is not in bold. Did you get my point or not? When this one gets in bold, what? IPGP, which is what? The interior gateway protocol communications between this one and the interior routers. Listen to this. I'm not sure here across, so that I need you. After this one communicate with this one, what does this one learn? This one learned that it can reach what? This network via this exterior, via this border gateway protocol. By the way, does this one know the distance to these? He doesn't know the distance. He only knows the distance. He only knows that there is a path to this network, a path, quote unquote, a path to via what? Via this exterior border gateway. He then relay this information to what? What is information? In words, verbally. What is he telling them? He is telling them, if you want to reach these networks, then send the packets to what? Send the packets to me. I know where to forward them. Clear? That is using what? Using the interior portal to generate a table with all the net IDs within the autonomous system, and they're this from what? The exterior gateway. So inside, they know the distance. This one, distance to this router. What is the distance to this router? What is the distance to this router? But those need to know these distances. Those don't need to know these distances. Those only need to know to what? To this autonomous system. So router communicate with other interior routers inside the autonomous system using an interior gateway, generate a table with all the network IDs within the autonomous system and their distances from the exterior gateway. But then what? Is given the same identity as the autonomous system to which it is attached. Every gateway is represented by the same identity as the autonomous system to which it is attached. If there are multiple border gateway protocols attached to the same autonomous system, they will have the same what? They will have the same ID. Don't confuse the IP address with the ID. It's just the what? ID, the autonomous system ID, the one that they are attached to. GP running in the exterior gateway makes contact with other exterior gateways and other misspelled with other autonomous exchange routing information with them. Clear? Exchange routing information with them. The routing information include what? Distances. It includes only what? It's only paths, as I will show you in just a second. The routing information exchange consists of a list of the network IDs system with their distances from the reporting exterior gateway. This is what internally. The routing information exchanged consists of a list of network IDs within the autonomous system with their distances from the what? The reporting exterior gateway. Reporting exterior gateway is the one collecting this information. This information is used by the exterior gateways to select the best gateway for forwarding the packets to a particular network ID and autonomous system. The functions of the PGP, which we'll see in just a second, all use request response messages, neighboring activation, neighboring reachability, routing updates, all of these things are functions of the PGP. Where their neighbors is, acquire them, terminate them if there is any problem with those routers. At which neighbor it can be what? Reached, which neighbor can it be reached, and of the routing, the update of the routing tables. Is a reliable protocol. Is a reliable protocol. It runs over what? It runs over what? TCP, which means what? You a TCP connection between exterior border gateways, to communicate that information about what? About the PGP. So PGP is a protocol, a reliable protocol that runs over what? TCP. Port number what? 179. What does this represent?
2 o'clock.
Port number. The well-known port number that is based on a routing method that is called what? Vector routing, rather than what? Rather than distance vector. Rather than distance vector, it's now what? Path vector. You don't care about what? Distances to all other networks within the autonomous system. You only care about what? A path. For example, you understand what I'm talking about. This is an example of what? A path vector routing table. He is saying the following. If the network ID is 1, then the next router is what? Is R1, and the path autonomous system 14, autonomous system 23, autonomous system 7. What does that mean? It means your packet will go through what? Your packet will go through multiple. These are the identities of the autonomous system. Number 2, the next router is what? Is R5, if ID 2. The next router is what? Is R5. And these are the autonomous systems that you go through. And I will show you again in the next set of charts a detailed example on this one here. The which a packet must pass are explicitly listed. The autonomous system through which path they are explicitly what? Listed. The path vector route is the destination network ID, the destination network ID, the next hop router, and the what? A path, which is a sequence of what? Autonomous system. A path of autonomous system to reach the what? To reach the destination. This is called what? The path vector table, rather than the distance vector routing table. Okay. Again, I will show you a detailed example in just a second. Each exterior router, again, upon receiving a message, does the following. It verifies that the in agreement with its policy. What does this mean? If a border gateway protocol receives an advertisement from another border gateway protocol, is located within the what? Located at another autonomous system, the border gateway protocol needs to what? Needs to verify that the advertised path is in agreement with its what? In other words, it does allow packet coming from what? From that particular autonomous system. So verify that the agreement with its policy, update the routing table by adding its autonomous system to what? And replacing the next router entry with its own. Why? They're replacing the next router entry with its own. In other words, let's see if you can help me.
So we have 5 minutes.
Thank you very much. Let's see if you can help me. Again, detailed explanation of the PGP, we will do it on Thursday. But let's understand this briefly here. What is this one? Is how many autonomous systems do we have? 4 autonomous systems. What is advertising? What is this router is advertising? To who? To its neighbor. Who is the neighbor of this guy? You notice, by the way, this one does not connect to this one. This one is, what is he telling them? He is telling them the following. Who is talking? The exterior gate. I can reach N1. Yes, I can reach N1. This is the network. How did you know about this? That's internal. That's the internal gateway protocol. Did you get this or not about this? He advertised. What does he say? I can reach N1. I am your next hop what? Router. Serving which autonomous system? Autonomous system 1. Does he tell them about the distances? Does not tell them about the distance. He just tells them, I can reach N1. I am your next hop route is 2, AS1. What is this one is advertising? What is this one is advertising? And QoS network. What is this one is advertising? He is advertising to their neighbor. What is he advertising? Each N1, which is this N1, I am your next hop router. Did you? R2 replaced what? R1. R2 replaced R1. Add. What did he add to the path? He added his own autonomous system. The path now is what? AS1, AS2, which means what? This one is telling this one, if you reach N1, if you want to reach, I am your next hop router, and your packet will go through who? 2 autonomous system. Autonomous 2 followed by what? Autonomous system number 1. What is this one is advertising to? You can tell me. What is this one is advertising this one? It's telling them, if you want to reach what? Remove this N1 here. If you want to reach the next hop router, R3, and what are the autonomous systems? AS3, AS2, AS1. In other words, this one is telling this one, your packet go through autonomous systems, 3 autonomous systems. Did you get this or not? Okay. If there is connectivity between this one and this one advertised to this, what will this one advertise to this? He will he can reach N1. The next hop router is what? R1, and only what? 1. This one might decide to go this way rather than to go what? That way. Why? Because this advertisement reach N1 through how many autonomous systems? 1 autonomous system, whereas this one is through how many? 3 autonomous systems. Did you get my point or not? Or not? All of these, by the way, no distances are involved. Just a path. Or what? A path is telling it that you can reach this network through what? Through this a series of autonomy A2, A1, and so on. So, clear? Clear? Okay. So each table, by adding its autonomous system to the path, every border gateway protocol will add its autonomous and replace the next hop router entry, with its own, because you are going to be the next hop.
So we are out of time.
Okay, we'll continue on time. Bring the next set of charts with you next time, please, so that we can see it clear.